Our next speaker is Donna Strickland. Donna is a Canadian experimental physicist born in May 1959 in the city of Guelph in southwestern Ontario. She received her bachelor's degree in engineering physics from McMaster University in Canada in 1981 and obtained a PhD in optics from the University of Rochester, New York in 1989. There, she and her doctoral supervisor, Gérard Mourou, developed a technique to immensely amplify the intensity of short laser pulses without destroying the amplifying medium, which was a severe limitation at the time for the achievable laser peak power. This so-called chirp pulse amplification technique, or CPA for short, was described in a 3 pages long scientific paper published in 1985. Donna was only 26 at the time. And it was Donna Strickland's first scientific publication and a subject of her doctoral thesis. Chirp pulse amplification revolutionized the field of laser science and led to new advances in many different fields, including medicine and the much publicized eye treatments. Donna Strickland is fascinated by lasers. She has worked at the laser division of the Lawrence Livermore National Laboratory and at the Princeton Advanced Technology Center for Photonics and Optoelectronics Materials. In 1997, she joined the physics department of the University of Waterloo, where she is currently a professor leading an ultra-fast laser group that develops high-intensity laser systems for nonlinear optics investigations. She was named a Fellow of the Optical Society of America in 2008 and has chaired several of its committees. In 2013, she serves as its president. Please join me in welcoming Donna Strickland on stage to tell us about the developments which led to this year's Nobel Prize.
So thank you very much. So I'm here to tell you about how light interacts with matter. And then when the light gets very intense, it changes how it interacts with matter. I'll tell you then how we made an intense laser, and by the time we were finished, we had to rethink how intense light interacted with matter. So to start, we first have to go back and see how does light interact with matter. So through the centuries, scientists wondered, was light made up of particles or was light made up of waves? And it went back and forth. By the end of the 19th century, scientists were pretty firmly in the light is a wave category. So they were doing experiments with different colors of light, shining it on material, and watching electrons come off the material. Now, when they shone the red light, and I'm only going to describe light that we see, the longest wavelength that we see with our eyes is red light, and wavelength is given by the distance between the crests of the wave. When they shone red light on material, electrons did not come off. When they tried to get the light as bright as they could, electrons did not come off. Now, when they switched to green light, which has a little closer spacing of the crests, electrons came off. But they came off with very low speed. They turned up the power of their green light, and more electrons came off, but always with very low speed. And finally, when they tried violet light, which is the shortest wavelength that we can see with our eyes, so the shortest distance between the crests, the electrons came off with higher speeds. And when they turned up the power, more electrons came off, but always with those same speeds. Now, this flies in the face of light being a wave. If you can imagine walking on a beach that's a stony beach, and if you just have small... See, I know, I talk so loud, I don't need a mic. So when you walk on a beach and there's stones and you just have little ripples in the waves, the stones don't even move. But if the waves are really crashing in, you will see those stones flying up the beach. And this is how waves would usually move objects. And so when we turned up the power of the light, we certainly expected that the electrons would fly off faster, and yet they didn't. So it's this man here, Albert Einstein, who probably thought of almost all of physics all on his own. What he won the Nobel Prize for, though, was explaining this effect. And so we in optics are pretty proud of the fact that this is what he won the Nobel Prize for. So what he figured out was that light actually is quantized in its energy. There is a minimum energy unit of light that we now call the photon. It's a wave-like particle. So what it says, though, is that the total energy in your light is then the energy of an individual photon multiplied by the number of photons. The other thing that he figured out then is that each photon has an energy given by this wavelength. And so I'm going to do an analogy because it's harder for us to feel the energy of light. So we'll use gravity that we all know about standing on the Earth, and that if we dropped a ball from higher up, it would be faster when it hit the ground. The higher up you can drop it. So now a red photon is a small photon. So we're going to imagine playing basketball with a child-size basketball net. And so if it's a red photon playing basketball, no matter how they try, even up on their tippy toes, they cannot reach that net to drop their electron through. And no matter how many of these childlike photons there are, the electron is never going to get through that basketball net. Now, if you have a green light, that's like an adult playing with a child-sized basketball net, and they can actually dunk through. But only barely. They're only standing slightly taller than the basketball net. And so when they drop their ball through, oops, we have to go back. You have to drop your ball. There you go. See, so slow. Because it's just slightly taller. But the violet photon is like your pro basketball player. They're the very tall people. And so they're well above the net. And when they drop their balls through the net, boom, a lot more speed. But it wouldn't matter how many of these violet photons they had. They would all be dropping at the same speed through the net, just more electrons coming off. So usually when people study the photoelectric effect, it's about quantum mechanics. But that's not what I want you to concentrate on. What it really told us about how light interacts with matter is that it's always one photon meeting up with one atom at a time, and they meet with each other. And if that photon has enough energy, more than the energy that the atom is holding onto its electron, it can then send the electron on its way. And when there's more photons coming, they interact with more atoms, but always one photon meeting one atom at a time. And that's how we understood how light interacted with matter through the beginning of the 20th century. And then along came this woman, Maria Gabriel-Meyer, the woman who won the second woman to win a Nobel Prize. Now, I'm not going to talk about her Nobel Prize winning work because I know nothing about it. I'm going to tell you what she did for her PhD in 1930. She published the paper in 1931, and I cited that 1931 paper in my own PhD. So I don't know why she thought about this, right? Maybe she brought her woman's way of looking at science and thought, why don't photons get along? Why don't photons want to work together, right? Because if two photons would just come into that atom at one time, they would share their energy, and two little red photons would have the same energy as one violet photon, and then there we go. It would have an electron come through with pretty high speed. This is what we now call multi-photon ionization, because there's more than one photon in the interaction. She didn't get to call it that. I don't know what she called it. It was all in German. So now we could understand that, but nobody had seen it. Don't forget, Einstein was actually sitting there wondering why the experimentalists were seeing what they were seeing. Maria Gabriel-Meyer, nobody had seen anything like this, so I don't know what made this woman think about it. But in fact, nobody would see this effect for another 30 years. It was Peter Franken's group at the University of Michigan, and I know I have a lot of Michigan people in the audience, that were the first people to see a multiphoton effect. Now, they were doing their experiment not with atoms that would eject electrons, but what happened was that 2 red photons were momentarily absorbed by an atom, and then when the atom wanted to let that energy go, it didn't let it go as 2 red photons. It let it go as 1 photon with twice the energy. So you'll see then that the wavelength here is half. Well, that looks less than half, but whatever. We'll call it a half. Can't have everything right. Anyway, so this is now what we call second harmonic generation, all right? And we now see it more routinely, but this was something to see in 1961. So then it begs the question, why did it take another 30 years to see what Maria Gapert-Meyer had predicted back in 1931? What was special about 1961? Well, it's already been mentioned in the previous talk. What was special about 1961 is that in 1960, the laser was born. So because I'm giving a Nobel lecture, I do want to honor all of the people that have won Nobel Prizes for the laser. Basov, Prokhorov, and Towns were really honored for developing the maser. The maser came before the laser, and the M is for microwaves rather than light in lasers. Technologically, it was easier to make a maser than a laser, and so that was done in the 50s, and they won a Nobel Prize. But it was the precursor to the laser. Art Shallow then won for laser spectroscopy later on, but he had a lot to do with understanding how a laser works. But I want to give credit to this man, Theodore Maiman, working at Hughes Aircraft. He's the one who won the race. There was a race on at the end of the 50s and into 1960. Who would be the person who would first demonstrate the laser? And it's this man, Ted Maiman. So 1960, the laser was born. And that's why Peter Franken's group could see this nonlinear optical effect. Now, why is that? Regular light, as shining on me very brightly here, sunlight or what have you, is like this bulb right up here. And in normal light, photons of every color is coming off. That's why it looks white. They go off in all directions. And they also don't talk to each other. They all go off whenever the heck they feel like it. No cooperation whatsoever. That's not how a laser works. A laser, as I'm using right here, and I'm going to shine on the wall over there, you will see that the light only goes in the one direction where I shine it. You don't see it going over there because the light's not going into your eyes. The light's going over there. So we already have it concentrated into one beam. You'll also see that the laser is just one color, and in the case of the laser pointer, just green. They also, the photons in the laser, all talk to each other. And when one's at a crest, they're all at a crest. And so each of these photons are going together, and so they are making themselves to be a giant wave. And a giant wave means the density of photons is greater. So let's go back and think about the linear case. Here's what they saw before 1960, just regular light, photons of every color, just in case you don't recognize them, those are the photons waving at you. And because there was no cooperation, the density of the photons is not very high. So also when you maybe take a lens and you think you're putting sunlight down to a point, I'll tell you it's not going to a point. We can only focus light down to a wavelength. So the light that we see is about a half a micron. The laser I built is 1 micron, so we're going to go with that. 1 micron is a thousandth of a millimeter. And so you can't focus your beam any smaller than that to concentrate your photons any better than that. But the size of an atom is much, much smaller. Now, because I'm standing in Sweden, I'm going to tell you that the dimension of an atom is an angstrom. But we're not really supposed to use that unit anymore. I'm sorry about that, my Swedish friends. We have to say that it's a tenth of a nanometer, all right? So this atom is actually 10,000 times smaller than you can focus the light. So when you blow up that atom, because of the concentration of photons, you're lucky to have one atom meet one photon. There's really almost no chance of 2 photons finding one atom at the very same time. But not true with a laser light. The laser light have all these single-colored photons happily shaking together. I don't know if mine are shaking together, but they should be shaking together. And so they pack in a lot tighter. And so you have some chance of seeing 2 photons in the volume of the atom at the same time. I want to credit Nicholas Bloomberg, the person who won the Nobel Prize for nonlinear optics. I'm also going to tell you that it took a long time for me to realize there was a difference in multiphoton physics and nonlinear optics, because I was at a conference celebrating 50 years of nonlinear optics. And I'll just tell you that people that study molecules and atoms, those are the atomic physics types, they say when they're watching the atom that they're doing multiphoton physics. Those of us who actually study light coming out, we're doing nonlinear optics. But to me, it was a very subtle difference. So this man won it for nonlinear optics. So here we go. We now have a chance of 2 photons. So this gets me to my PhD. Gerard gave me a paper written by Stephen Harris of Stanford University. And he had this idea that lasers were sort of stuck in the visible to the infrared, but we might want this wonderful type of radiation in high energy photons, past the violet, ultraviolet, maybe even out to the extreme ultraviolet. So for that, we can't just do second harmonic or even third harmonic. He had come up with, theoretically, ways to maybe have 15 photons be grabbed by one atom and release a photon that's got 15 times the energy. So Gerard said, you know, do you want to do that? Just think about this paper and see what you want to do for your PhDs. So I came up with a way to maybe in twice ionized nickel, I would be able to absorb 9 photons. So that was supposed to be my thesis, never got to it. Anyway, that's why I needed a high-intensity laser, and so a laser itself was not going to get 9 photons squeezed into an atom. We needed an intense laser. So how did we do it? So first, I want to go back to this laser that I have in my hand. The power of this laser is about 1 milliwatt, or 1,000th of a watt. I can make it a pulse, 1 second long pulse, by stopping it, opening it up, and shutting it 1 second later. Now, in that pulse of light then, because power is energy per unit time, if my time unit is 1 second, that's 1 millijoule of energy. Now, I can also shine that on my hand, and it doesn't hurt at all. I won't shine it in your eyes, but I'm going to put it in my hand and tell you that that millijoule hitting my hand every second doesn't hurt at all. And yet my paper, that was only 3 pages long and got me this Nobel Prize, only had 1 millijoule of energy created. It's also all the energy you need to slice your eyeball up. It's all the energy you need to cut glass. And yet it doesn't hurt my hand at all. And so what's the difference? Well, if I had shone that 1 second pulse of light out to where the moon is, and I have no idea where the moon is, but and I couldn't do it anyway, it would be, the beginning part of the pulse would actually be, this is always the one that doesn't work for me, let's go. Oh, there we go. The front part of the pulse would actually be 2/3 of the way to the moon before the end of the pulse would leave the laser. That's how fast light travels. And so now in our 1 second pulse, we have 1 millijoule of energy in this 1 second long pulse of light. Now, what did the Franken group have in order to see that very first multiphoton effect? They had light that was 1 millisecond long, so that's 1,000 times shorter, still 300 kilometer long line of light. I will tell you they had more than a millijoule, they had a joule. So they had 1,000 times shorter and 1,000 times more energy. And then with that millionfold, they were to see the odd time an atom grabbed 2 photons at once. The laser that we built in Rochester, though, was shorter than that. We squeezed it down some more. And in fact, we squeezed it down so that 1 millijoule of energy was in 1 picosecond, or just 1/3 of a millimeter. So all of the many photons that would have stretched 2/3 of the way to the moon were squeezed down till they were just 1/3 of the millimeter. We packed those photons in. So I know that my supervisor and colleague will be coming up here and telling you all the amazing things this laser has done for us. I'm sure even some of them are going to be, he's going to talk about things going on in space. But I'm going to bring us back to Earth. I'm going to bring us to Rochester, New York in the United States, where I did my PhD at the Institute of Optics at the University of Rochester. And I did my research here at the Laboratory for Laser Energetics, and there I am back in the day. Now, inside this Laboratory for Laser Energetics was this absolutely beautiful dye laser. It was red and green, and as I've said, it just seemed like a Christmas tree to me, and I wanted to work with Gerard in this wonderful group. It is a dye laser. A dye laser is a type of short pulse laser. In fact, this laser, the pulses were actually 10 times shorter than what I'm talking about, so only 1/30th of a millimeter long. So we had short laser pulses. Problem is, dye lasers don't like to grab their energy and hang on to it, and so you can't get a big energy dye laser. So you can have short pulses, but the reason that the Laboratory for Laser Energetics was there was to study laser fusion. And to study laser fusion, you need a big laser. And they had a big laser. This was known as the Omega laser. It was 24 beams. And it could produce a kilojoule of energy. Not a millijoule, a kilojoule. That's 1,000,000 times more energy. So in the laser lab, we had short pulses and we had big energy lasers, but we couldn't put them together. More than one problem. One, the dye laser had red photons, and this one wants to amplify infrared photons, so they wouldn't have spoken to each other. But there was a bigger problem. When people tried to put slightly short pulses even into these lasers, what they found was that the rod would actually get drilled all the way through, and you were left with a very expensive piece of glass that wasn't any good. So they had to stop trying to put short pulses down their laser rods because these nonlinear optical effects were happening inside the laser rods, and they were drilling holes all the way through them. So that was the conundrum that we were in the early 1980s. And then Gerard had his beautiful idea. So there are no pictures because I hate having my picture taken. I've had to get used to it since October 2nd. But there are no pictures of Gerard and I together. So we were at a meeting a few years back and took this picture. So this is a very simple, beautiful idea. This is what we want here. We want a lot of energy. We want it in a very short pulse. We just don't want that in our amplifier. So if we don't want that in our amplifier, what can we do? Just start with a short pulse, stretch it and make it a long pulse, amplify it up, and then at the end, compress it all the way back down. And here you have what I like to call a laser hammer. So now, how did we actually do it? We're going to go back to this lab because this was the lab. Now you'll see I've changed the title of it, even though I'm showing you the very same laser. And so the green beam is actually not a green laser. This is the laser back here. It's infrared. You can't see the beam coming out of the laser because it's infrared and we can't see it, neither can the camera. The kind of mirrors that we use in a laser lab direct just the color we want to direct. And so this green light bent at this mirror, but the infrared came on through. It would have gone to a beam dump to protect all of us from feeling the heat of that very strong laser. And so that laser had the same wavelength as the big neodymium glass amplifiers that we wanted to use. So that was the laser I was to use. You can also see there's simply no room in the inn for me. This was one packed lab. But they shoved me into that corner where the infrared came out, and there I am in 1985 with 1.4 kilometers of optical fiber. So why did we need this fiber? Well, there was one advantage of it. It's not why we needed it. Because there was no room for me here, once we had the light going down the fiber, that fiber then went through the air duct down the length of the Laboratory for Laser Energetics, where I built the amplifier at the other end of the building. That was one thing. But the two other reasons that we needed this fiber is that the laser that pumped the dye laser was not as short as we wanted, and we needed more colors. I'm going to explain why we needed more colors. I don't have time to tell you what nonlinear optical effect made the colors. You'll just have to believe me that it did. And then this is the component, though, what we really needed the fiber for. This was our pulse stretcher. So first, to understand pulse stretching, we have to know, why do we need a lot of colors in order to make a short pulse? If you watch just one of these colors, and we can just do the red one, you see it goes along there, a red wave would go on forever. Now, if you take more colors and you say that you want all of them to start here, you'll see then each wavelength starts to come apart. You don't have to go very far until some are peaks while others are troughs. And so if one wave's a peak and the other wave's a trough, they cancel each other out to be nothing. And so the more colors you can add in, the quicker you will get to where it's 0. And so the more colors you have, the shorter pulse you have. So we created the colors in the fiber, and now it's time to stretch it. How does that work? Well, in the way that light interacts with matter, I said that the red photons have the least energy. When they meet up with their atoms, they sort of shake hands, but then they say, we have, have nothing in common, off you go. So they actually run faster than the green, and by the time it's a blue photon, they're actually considering some time, do we or do we not want to interchange our energy? And it takes a little longer for that blue one to decide no and keep on going. So now if you go down fiber, you will see that the red ran, the green walked, and the blue sort of crawled. And if you go down something like 1.4 kilometers of fiber, well, the red ran, the green, and now you have a long pulse. So I want to explain the name of chirped pulse amplification. A bird's chirp is called a chirp because the sound frequency changes in time through the note that he's making. So you'll see that the way to get a long pulse is to have the red frequencies out first, and then the green, and then the blue. So through our laser pulse now, the frequency changes, and that's called a chirp. It's called chirp pulse amplification because this is now our stretched pulse that we want to amplify up. So how does the amplification work? So it's some material that has some atoms and sitting there, not doing anything. They have to be excited by some kind of energy source. The original lasers and the laser that I used flash lamps. You'll see that it lights up most, not all, most of the atoms. And a good storage medium will hang on to that energy and stay excited until a photon decides to come by. So then you can have a photon come along, boop, and meet up with an atom. And because we've excited these atoms so they have the very same energy as the photon that we're going to try to amplify, they meet each other, and the photon says to the atom, I'll take your energy with me. And now we have 2 photons, and that atom lost its energy. Those 2 photons are marching in step together, and they meet 2 more atoms, and now we have 4 photons, and we've given up 2 atoms of energy, and by the end, we'll have 8 photons, and they've given up the 4 more atoms of energy. Now, this is actually very wasteful because you'll see that by the end of it, we've left most of the energy there in the amplifier. So that's a complete waste, and we don't want to do that. If it was a laser, we would put mirrors on either end and have it go back and forth until we steal all of that energy. And this is then why we have to keep building huge lasers if we want a lot of energy. The laser rod itself determines the energy per unit area that you can take. And if you want to grab it all, you actually have to put in almost that much energy to start, to snowplow through and take the energy. So each amplification gets a certain energy per unit area. If you want more energy, you must make your beam bigger, you must make your amplifier bigger, and you plow through again. The other thing I want to point out then is that the laser material decides what's the energy per unit area, but the nonlinear things that can cause damage is the energy per unit volume. So once you know what laser you're using, that determines how much you must stretch the pulse so that you keep it below any kind of damage threshold. So that's why we would have to chirp based on the type of laser that we used. So now that we're amplified up, it's just time to compress. And so with a pair of parallel gratings that act like prisms that send different colors of light out to different angles. And so if you watch the path, and you'll see the red, because it was stretched, is further ahead than the green, and the blue is trailing, that when it comes off this grating and each goes on their own angles, that by the time the blue one has managed to get to the grating, the red one had to travel all the way back here and could get here, so that when they all leave the second grating, they're all going together, and we've put all of the photons back together in time, and so we have a short pulse. So then it was just time to measure it. My colleague Steve Williamson came into my lab with history camera one night, and together we measured, did I or did I not actually have an intense short pulse, and the answer was yes. So we were very happy that night in 1985. So what did we do with it? Well, remember, I wanted to study harmonic generation. That proved too difficult. So we're going to go back to the idea of multiphoton ionization. And we thought that we would just kick that electron and give it so much energy that it would be able to come out of this well that it sits in the atom. And so all those photons would come up and kick that electron out. That's what we were expecting to see, but that's not what we saw. We had made such an intense laser that the photons were packed in there so tight, we no longer had to worry about them being photons. It was back to being just one giant wave. Now, although it's a short pulse wave, so each crest gets a little bit more intense and a little bit more intense. And so what happens when you have a giant wave is that it interacts with the atom that was sitting in its potential. My head can be the electron. And the wave would push it this way, and then the wave would push it that way, and then it pushed it more, and it pushed it more. And finally, it pushed it so much that electron was allowed to go out of the well. But not only does it go out of the well, it goes out of the well into this giant electric force. And it is like a cannon being shot right out of there. Now, it can either leave, or in 2 femtoseconds, that light's towing back, and it may be driven right back to the ionic core. It just depends. And I'm not here to tell you about what happens. Oops, let me show you. Did I show you at least the electron going out? No, there we go. The electron at least went out. I'm going to leave that to my PhD supervisor, colleague and friend Gerard Moreau to tell you about what we understand now about the new understanding intense laser light interacting with atoms. And I will just thank all the people. I want to thank the people that built the original CPA with me, of course, Gerard, but also Steve Williamson and Marcel Bouvier, who are here with me today. Gerard likes to tell people how I said that CPA would not be a good PhD project, or thesis, could not be my PhD thesis. I don't know why he tells the story, because I was right. It could not be. I had to do science with it, which I did multiphoton ionization, and I want to thank the gentleman that helped me with that project as well. And finally, I would like to thank the creative team at the University of Waterloo for making these wonderful slides for me. Thank you very much.